Normal distributions and the empirical rule. Part 1. Normally distributed data sets. One very important distribution, which occurs frequently in real life, is the so-called normal distribution. This continuous distribution is seen in the measurements of heights, blood pressure, exam scores, the weights of items produced by machines, among many other situations. The frequency curve of the normal distribution is called a normal curve, and it has a distinctive bell shape, as shown below. Different normal distributions may have different means and different standard deviations, but they all share a number of common properties. So here are the properties of a normal curve. Here's our normal curve. Property 1. The curve is symmetric about the vertical line through the mean. So we see here this vertical line is a line of symmetry. It's like a mirror line. We have exactly the same curve on the left of the line as we have on the right of the line. And this is where we will find the mean. This is the symbol for mean. It's like a U with a little line coming down in front. Thus, 50% of the data, and hence the area under the curve, lies on each side of the line. So 50% of the area under the curve lies to the left of the line, and 50% of the area of the curve under the curve lies to the right of the line. And this represents 50% of the data is to the left, and 50% of the data is to the right. Property 2. The mean, the median, and mode of the distribution are equal. So the mean, the median, and the mode all lie right here at the very center, the line of symmetry. And property 3. The percentage of the data that lies within 1, 2, and 3 standard deviations of the mean is the same for all normal curves. So we can see here that this is the mean, and from here to here is 1 standard deviation, which is why this is called mean plus 1 standard deviation. So this symbol here looks like a 6 is a symbol for standard deviation, or it's like a circle with a little tick off the top. And if from here to here is 1 standard deviation, then this is the mean minus 1 standard deviation. Within 1 standard deviation of the mean, approximately 68% of the data, and hence the area, lies within 1 standard deviation of the mean, i.e. between the mean minus the standard deviation and the mean plus the standard deviation. So if we have looked down here at our normal curve, we know that this is the mean, and this dotted line here represents the mean plus 1 standard deviation, and this dotted line here represents the mean minus 1 standard deviation. So from here to here, this area in yellow, this is actually 68% of the area. And 68% of the data lies within 1 standard deviation of the mean. This is a summary of what is known as the empirical rule. Within 2 standard deviations of the mean, approximately 95% of the data, and hence the area, lies within 2 standard deviations of the mean, i.e. between the mean minus 2 standard deviations and the mean plus 2 standard deviations. So this dotted line here is the mean plus 2 standard deviations, and this dotted line here is the mean minus 2 standard deviations. So from here to here represents 95% of the area. So again, according to the empirical rule, 95% of the data lies within 2 standard deviations of the mean. Within 3 standard deviations of the mean, approximately 99.7% of the data, and hence the area, lies within 3 standard deviations of the mean, i.e. between the mean minus 3 standard deviations and the mean plus 3 standard deviations. So it's hard to see, but this dotted line here, which would be very close to the end of the curve, is the mean plus 3 standard deviations. And this one here is the mean minus 3 standard deviations. So this area here is 99.7%. So 99.7% of the data lies within 3 standard deviations of the mean. So again, this is the empirical rule. This is known as the empirical rule and can be used to obtain estimates of the number of results in different intervals. So it's important that this is learned off by heart. So the frequency curve of the normal distribution is called the normal curve. So here we have the normal curve. And again, this is just a summary of what we went through. So if this is the mean, and this dotted line here is the mean plus the standard deviation, plus 1 standard deviation, and this is the mean minus 1 standard deviation, and if from here to here is 68% of the area, then half of 68, so 68 divided by 2 is 34. So this must be 34%, and this must be 34% as well. So if from here to here is 95% of the area, so if from this dotted line all the way over to this dotted line is 95% of the area, then 95 minus 68 divided by 2 gives us 13.5%. So this must be 13.5% and this must be 13.5%. And then if from here to here is 99.7% of the area, so from here to here is 99.75% of the area, then 99.7 minus 95 and divided by 2 gives us 2.35%. So from here to here is 2.35%, and from here to here is also 2.35%. It would be a very good idea to get familiar with these numbers. 2.35% for the tails, 13.5% for the middle, and 34% for the area beside the mean. It would be a very good idea to get familiar with these because you will use them quite a lot. The curve can be used to find the probability that x lies between two given values. Although, with the empirical rule, we are limited to values which are related to the mean and the standard deviation. The areas under the different sections of the curve give the probability of that interval. The lifetime of a particular type of battery is normally distributed with a mean of 20 hours and a standard deviation of 2 hours. The random variable x stands for the lifetime of a battery. Part 1. Describe in words what is meant by P. The probability that x is greater or equal to 20 but less than or equal to 24. So the probability that x is greater or equal to 20 but less than or equal to 24 stands for the probability that the lifetime of a battery chosen at random lies between 20 hours and 24 hours. Part 2. Calculate the probability that x is greater or equal to 20 but less than or equal to 24. As the mean is 20, that was given in the question, and the standard deviation is 2, again given in the question, then 24 hours is going to be the mean plus 2 standard deviations. Now where did this come from? The mean plus 2 standard deviations. Well, we know that the mean is 20. And we know that our distribution is normal. So we can draw our bell-shaped curve, and we know we can draw a line of symmetry down the center, and this represents the mean, which is 20. If our standard deviation is 2, then this dotted line here, which is the mean plus 1 standard deviation, must be 22, because 20 plus 2 is 22. And then this dotted line here must be 24. Because we're going from 20 to 22 to 24, And this must represent the mean plus 2 standard deviations, because 20 plus 2 plus 2 is 24. So this represents the mean, which is 20, plus 2 standard deviations. So 2 times 2, which is 4, so 24. So now we know where this came from, the mean plus 2 standard deviations. From the diagram below, or across, the area under the curve between the mean and the mean plus 2 standard deviations is 0.34 plus 0.135, which equals 0.475. So where did these numbers come from? So this is our previous slide. We said if from here to here is 68%, then from here to here must be 34%. So from here to here is 0.34 or 34%. And again we said from here to here is 95%. And 95 take away 68 divided by 2 leaves us with 13.5%. So this area under the curve is 13.5%, and this area under the curve is 13.5%. So we're interested in from here to here, which is 13.5%, which is a decimal, is 0.135. So that's where these two decimals came from. And adding them together, we get 0.475. So from here, from 20 to 24, we have 0.475. So therefore, the probability that x lies between 20 and 24 is 0.475. So the empirical rule is useful for the following: getting a rough idea of the percentage of data in certain intervals, providing a test for outliers. An often used definition of an outlier is a result that lies more than 3 standard deviations from the mean. Providing a test for normality. If we find that a sizable percentage, 3% or more, of the probability lies more than 3 standard deviations from the mean, then the distribution cannot be normal. Part 2. Normal probability distribution. A probability distribution, which has the same distinctive bell-shaped curve as a normal data distribution, is called a normal probability distribution. This probability distribution occurs very often in practical situations and is of great importance in the theory of probability and statistics. All normal probability curves share the same properties listed above for normal frequency curves, i.e., symmetry and the empirical rule. So symmetry and the empirical rule also apply to normal probability distribution. They also satisfy one extra property. So this is a property that only applies to normal probability curves. And that property is that the area under the curve is 1. So for example, if this curve is a normal probability curve, then this area underneath it must all add up to 1. Like the area under all probability curves. The diagram below shows a normal probability curve for the probability distribution of the normal random variable x. So to summarize, normal distribution, bell-shaped graph, curve or function. The mean, median and mode of a normal distribution are equal, and they all lie here. The area under the normal curve is equal to 1. Normal distributions are denser in the center and less dense in the tails. That's how they're bell-shaped. So denser in the center and less dense at the tails. Normal distributions are defined by 2 parameters, the mean and the standard deviation. Part 3. The normal distribution as an approximation to many discrete distributions. The normal probability curve, which is a continuous curve representing the probability distribution of a continuous random variable, is a very good approximation to many probability histograms, which represent the probability distribution of a discrete random variable. So just a reminder, continuous data can take any value, whereas discrete data must take a certain value. So for example, a good example to describe discrete data would be the number of people. You can have 3 people, or 4 people, or 5 people. You can't have 3.5 people, or 3.25 people. Examples of continuous data would be height, weight, time, length, distance, speed, and so on. For example, if the random variable x represents the number of heads obtained when a fair coin is tossed 10 times, then the probability distribution of x, i.e. the probability that x is equal to or, for or equal to 0, 1, ... up as far as 10, is called a binomial distribution. So again, for example, if you're tossing a coin 10 times, you can land on heads 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 times. You cannot land on it 5.5 times or 4.3 times and so on. So this is why it's discrete. If we plot the probability histogram for this distribution, we can see that the shape is approximately the same as a normal curve, which is the dashed curve indicated. So the green bars represent the discrete histogram, and the dotted line, the dotted curve, is the normal curve. And we can see that it is very, very, very close to the same shape. If we toss the coin many more times, for example 100 times or 1,000 times, the shape of the histogram gets closer and closer to a normal curve, because the bars would get thinner and thinner and thinner the more that we add in. At the moment we have just 10 of them, but if we had 100 or 1,000 they would be much, much skinnier. And instead of having this jagged shape, we would have what is very close to a smooth curve. Not all probability histograms are approximated by normal curves, but many of the most important are.